Alrighty, let's see if this works. Okie dokie. Wow, it actually seems to work. That's awesome. Okay, cool. Alrighty, good morning, everybody. Since this is a new computer that I'm using today, can you guys hear me with this one? Just want to make sure. Okay, cool. So, before we go ahead and get started, does anybody have any questions from last time? Hi, little dude. Anything at all. So, then, while you guys are potentially typing out your questions, let's go ahead and do some practice. We talked about atoms, right? And different types of, we learned about isotopes and ions and how we can identify subatomic particles associated with each of those. So let's just go ahead and do a few more to practice. So let's say that we have an atom with 17 protons. Oh, good. Oz is going to start barking as soon as class begins. That's always a good sign, right? Oz, sweetheart, come here. I want you guys to come up with the symbol in AZE notation for this particular element, and we're going to do a second one here. We're going to have to deal with them a little bit more this week, since in Ridgecrest I don't have as many options to hide the dogs away from where I am streaming, so we'll see. Okay, so there's one for us, and then let's do another one. Be good, mister. How about we do... I'm gonna need a periodic table. Let's see. Do I have one lying around here? Okay, while y'all are working on that first one on the left, I will go get a periodic table. Oh, wait, no, hello. We have technology here. What am I doing? Alright, let's see what something reasonable about barium would be. Okay. And let's just say with this one we have 70 neutrons. Just something reasonable. May of course not exist, but I want something to be somewhat reasonable for you guys. I don't want to just come up with atoms that could, never exist. So, what do we think about the first one here? Sure, relax, dude. Yeah, I like that. About to sneeze. Oh, come on. There we go. Man, the smoke here is killing me. Sucks. But we'll survive it, right? Okay, so we've got some of the stuff here. Now, Sherry, out of curiosity, did you know that this would be chloride or chlorine? Out of curiosity. And with that one, I'm going to disagree with you that 20 is the atomic number. Try that one again. Okay. 17, that's better. That's what I'm looking for. Very nice. Okay. I'm just trying to pull this up on the other computer here. Scrambling this morning to get this all, set up. So, okay. Now do the second one. By the way, we knew that chlorine, in this case chloride, would be a -1 charge because there's one more electron than proton, right? Remember the charge is proton minus electron. So 17 minus 18, -1, and that's where that charge is going to be on the top. Okay? So, start working on the second one while we get this going. Da-da-da-da. Yeah, that's okay, Sherry. Very often we're going to see chlorine in its chloride form. We're going to learn about that in a few chapters, but totally normal to do that way. So chlorine is, by the way, just so I can tell you the difference, chlorine is just the element by itself. Chloride is when it has that -1 charge. So you were correct, whether or not you knew you were. Okay, let's work on the next one here. So we're missing a few things. We don't have our protons or neutrons quite yet. We don't have the stuff to the left of the element symbol either. So let's go ahead and get those up there. Okay, let's see. I had to look at the periodic table too because nobody remembers this stuff. Okay, so it looks like barium is number 56. It's in the 6th period of the periodic table and the second group. So I'll tell us right there that number should be 56. And I'll let you guys do the rest. Though it seems like only the two of you have woken up this morning, but that's okay. The rest of y'all are silent watchers. That's okay. While you're doing that, by the way, just to clarify, a lot of you were kind of worried about participation and stuff. Again, this is a state requirement that's fairly new, so I do not want to drop anyone from the course, so, but there are things that I have to do, so, obviously all of you are okay. 68, huh? Where did 68 come from? And what is 68 for? Are you looking for electrons? In that case, I would not say 68. You have the right idea, but take a look on the left there. Look what charge is equal to. Yep. But that's okay. This is a good time to do it. So you guys actually have your exam next week, right? So on Monday. So, oh, am I? Okay, let's see. What can we do about that? Alright, let's try that. Does that do anything better? I know what I can do. Okay. Is this how about now? Are we still echoing like horrible? Yeah, so I had to like throw all my stuff into a suitcase last time I drove up here. So I do have my like good mic. I like that, Valerie. Yes, for sure. How's the echo situation though? Are we better with this? Still echoing, huh? Okay. Outer space. Okay. So let's see here. Is that because I have this thing going? Okay. Well. I could try to swap the mic out, but let's just deal with it for now. Sorry. Oh, okay. Well, it could just be like crappy internet because crappy internet. So whatever. We'll just pretend that it's not so bad. By the way, your electrons. Yeah, you noticed this by the way back there, but yeah, you want to use the. I pushed my mute button on the laptop that I'm using right now. Since again this is like not my normal setup, so and I also got rid of the desktop audio on the streaming thing that I'm using, so I figured those would be my best shots at fixing any particular echoes, but who knows. Okay, any questions on these two? Yeah, very nice, 54. Alrighty. Then in that case, have we talked about atomic mass yet in this class? I'm sorry, I always get confused because 101 is like, they're essentially like a week ahead of you guys, but it's hard to remember, what I've talked to who, so. So like, did we learn where this number 79.904 comes from in our bromine, for example? Have we talked about that yet? Hush, caution, relax. Okay, so in that case, I will tell us that bromine exists as these two isotopes in nature, right? And so remembering that protons and neutrons have roughly a mass of 1 atomic mass unit, this is just approximately 79 atomic mass units. Let me just write atomic mass unit again. And this one is roughly 81 atomic mass units. Okay, yeah, you'll be, a lot of the sciences do have overlap, but I'll just teach you it here. We're not going to worry about calculating it, but everyone always wonders, like, why the heck does the periodic table say 79.904? And so it turns out that this number here is what's called an atomic mass, whereas these were mass numbers, which are roughly what are called isotope masses. And so we're going to see that the atomic mass, let's use purple, why not? Atomic mass is going to be the weighted average of all isotopes. Of an element. So some elements just happen to have, like 10 stable isotopes, some have 7, some have 3. Bromine particularly just has 2. So the math makes it easy for me to show you why it is that way. So it turns out that scientists have done calculations for us that bromine 79 here is roughly 51% of all bromine atoms. And bromine 81 is about the other 49%. And so we're going to see that if we take this 51% times bromine's mass number, you're not going to have to do this calculation in this class, by the way. I'm just showing you where it comes from. And this is going to be roughly equal to that 79.904 that you're going to see on the periodic table. It will be slightly different because, like, if you were to actually do this calculation, because these percentages are, pretty crappily, just like it's not really 51.49, it's like 50.942, or there's more sig figs here. I'm just kind of rounding, and then the actual isotope masses are a little bit less. So bromine 79 actually has an isotope mass of something like 78.9 or whatever. So just for other reasons. So just a little example here. This number we're going to see on the periodic table, that's our atomic mass, and it's calculated by being a weighted average of all the isotopes of an element. And what this means is that of a large sample of bromine in this example, bromine atoms, the average mass per atom is 79.904 AMU. While each atom in reality is not going to be 79.904, just the average, statistical probability is that each atom will be, on average, 79.904 atomic mass units. All right, and that gives us a way to bring atomic mass units into real-life units. So atomic mass units are super small. They're like 10 to the negative 23rd kilograms or something, super small. We're going to see that we're going to have a way to kind of bring stuff from atomic scales into real-life quantities, stuff that we can actually use, right? So it turns out that we have, in science, decided, we've defined a unit based on these atomic mass units. We've designed a real-life unit to kind of correspond with it. So here is a definition for you. Carbon-12. We're going to see that 6.022 times 10 to the 23rd of these carbon-12 atoms is exactly 12 grams of carbon-12. And this number, again, mathematically calculated, it is one you will become very familiar with throughout your chemistry journey. But we're going to see that this magic number here, the crazy number that you see there, is going to be extremely useful for us. So 12 grams of carbon-12, by the way, would be like a you know, if you had an isotopically pure like chunk of charcoal, it would be a pretty small chunk. Like, I don't know, maybe the size of like a die, like dice, one die. So a pretty small amount of carbon in terms of like, real life stuff. But that is actually, 6, what is that? Quintillion? I don't know, 6 something hexatillion, gajillion, bajillion atoms within that chunk of charcoal. So we're going to see that this number, which is called Avogadro's number, is going to be our fancy way of getting in between individual atoms and real-life quantities. So again, 12 grams is something we could use, but nobody is ever going to count out that many carbon atoms, right? Like, that's just absolutely ridiculous. The amount of time you would have to spend to count all those, forget it. Yeah, like, artist charcoal would be, I don't quite know how big those are, but 12 grams is not a lot. If you think about it this way, a shot glass full of water would be about 45 grams. So think about like a teaspoon of water maybe, and that would be probably the kind of the volume-wise how similar that would be. So if you think about a teaspoon of water being about 15 grams, 12 grams of charcoal, like pretty small quantity, right? So we're going to see that grams are going to be, of course, something we can use, but already, like, just imagine counting all of those atoms. Forget it. Nobody wants to do that. So because we see that this atomic mass quantity here is, the average mass for an entire large sample, of course, 6 times 10 to the 23rd is a huge sample of atoms, right? So we're going to see that by contrast here, 6.022 times 10 to the 23rd atoms of any element is going to be equal to the atomic mass of that element in grams. So what that means is that if we had that many bromine atoms, that would be equal to 79.904 grams of bromine. Or, if we were to look at another element, let's say, platinum. Platinum has an atomic mass of 195.084. Let me just write that down before I forget it. I've already forgot it. 195.084. Okay. 195.084 grams. Platinum. So that would be the same thing. So all those platinum atoms would be equivalent to their atomic mass in grams. Okay, and nobody, by the way, nobody likes to write out this number so many times. We have a better way to talk about it. We're going to see that this number is also going to be called a mole. So everyone likes to make that kind of joke where this is Avogadro's number, and now we're going to talk about moles. And of course, there's your guacamole-like type of pun you can make. Go ahead, have fun with that all you like. So we're going to see that 1 mole of platinum atoms is also going to be equal to the same thing. 1 mole is just 6.022 times 10 to the 23rd. And let's see, how about another one? We can also see that 1 mole of I don't know, hydrogen atoms. This is going to be 1.008 grams of hydrogen. And that number is just from the periodic table. Hydrogen is one that we're going to work with a lot, especially if you go into Chem. So I've rounded it there, it looks like, according to this particular app, which has more sig figs than I do. But that's where I got that 1.08 from. Okay, so a lot of students kind of get scared by this, but if we think about other terms that we've heard about, we might have heard, 1 dozen sulfur atoms is just 12 sulfur atoms, right? Nothing crazy there. Or if we had 1 gross of sulfur atoms is 144 sulfur atoms. Same thing here, 1 mole of sulfur atoms is going to be equal to excuse me, 6.022 times 10 to the 23rd sulfur atoms. So it's just like another word, just like dozen or gross or ream or score or whatever, these like old units. Bushel, I don't know, actually a bushel is not really that's like a volume, I think. Anyways, same idea here. So it's just another word for this crazy big number that's going to allow us to work with this, to work with atomic quantities a little bit more easily. So, that being said, let's go ahead and see what else we can find out. So we see that this atomic mass stuff can give us information about the mass of a particular number of atoms. But what if we had a molecule instead? For example, something like this molecule you might have seen before. And let's say if we wanted to see how much would 1 mole of water weigh? We could do that. I mean, technically, right, we would have to say, okay, that's going to be, so 1 mole, okay, let's go back. If we had 1 dozen water molecules, that's the same as saying we have 2 dozen hydrogens and 1 dozen oxygens, right? Just to step back for a second, just so we are all understanding about chemical formulas. So 1 dozen water molecules is made up of 2 dozen hydrogen atoms and 1 dozen oxygen atoms. So hopefully that is pretty clear. And so, if we had 1 mole of water, that's 2 moles of hydrogen and 1 mole of oxygen. And so, if we know that each mole of hydrogen was 1.008 grams, and 1 mole of oxygen was 16 grams. Again, I've gotten that number from the periodic table. This particular, maybe it's going to be like 15.9999999, whatever. Yeah. I'm going to just say 16 because we don't need all those sig figs right now. Okay, so I've got those. And so 2 moles of hydrogen would be that many grams, right? If 1 mole is 1.008, 2 grams is just 2 times that. And so therefore, if we put these guys all together, we're going to see that 1 mole of water is going to be equal to the sum of each of the atoms that make it up. So we added up together 2 hydrogens and 1 oxygen. So we took the atomic mass of hydrogen, multiplied by 2, and then we added to it the atomic mass of oxygen, and we got the mass of the molecular mass of water here. This is what is called a molar mass, or molecular mass, molecular weight. You can also say formula mass, formula weight. Technically, that one is a little bit more precise, especially if we're talking about ionic compounds. But very often, we're just going to hear molar mass. That's the one that I typically use, what most people typically use. However, all of these other terms mean exactly the same thing. So all of these refer to that same idea. Okay? Let's do some practice with this. Let's see if we can find what is the molar mass of CO2, carbon dioxide. So in this case, our molar mass is going to be equal to carbon plus 2 times oxygen, right? So we would go to the periodic table. We would say, okay, carbon is 12.01, and oxygen is 16. Again, just from the periodic table, I'm skipping that idea. I'll just write that here for people who don't listen. So these numbers are both from the periodic table. And okay, so if we go ahead and add this up, we're going to get 44.01. And in case you're wondering about units here, the units are either going to be grams per mole or AMU. Grams per mole and AMU are the same unit. Let me write that as well. By the way, the abbreviation for mole is MOL because why not? Let's just drop one letter from it and abbreviate it for some reason. So grams per mole and AMU are going to be the same unit. Okay? Oh my goodness. It begins. I think he heard something outside. Alright, I'm going to put a problem for you guys while I go figure out what's bugging them, and hopefully, well, you know what, they've stopped, but let's do it again. Nope. Now they started Oz barking. Let me give you something a bit harder to work with. This would be glucose. So, you guys calculate it. I'll be right back with a naughty doggo. Sorry, I found the perpetrator. That's right. I know you're very cute, and you're old, but that's not an excuse for being naughty. Okay, so how are we going to do this? Just like before, our molar mass is going to be 6 carbons plus 12 hydrogens plus 6 oxygens. And look at me, I've already got these numbers for myself. Again, these ones I work with all the time. These are like the big 3 elements of organic chemistry, so I, of course, have these memorized, but you do not need to memorize these, of course. So at any level of chemistry, you do not need to memorize them. We have periodic tables. It's kind of a waste of brain space to memorize them. But if you work with them enough, you'll probably end up memorizing some of them anyway. You put that all together, it's going to be about 180.2 grams per mole, or 180.2 atomic mass units. Either one, depending which unit you want. Again, they're the same unit, so interchangeable. Okay, you're probably wondering about sig figs with this stuff. I'm just going to tell you, don't worry about sig figs with molar masses. Okay? Typically, just give like 4. 4 is usually a good number. All this right here. Don't worry about sig figs here. So we'll be okay. These aren't really measured quantities, so these are all just kind of like theoretical numbers, so we don't have to worry about sig figs for this. So typically use about 4, so that would be fine. Or just keep whatever's on your calculator, you'll be okay. Okay, do we have any questions about these? So while you are coming up with questions, I will just go ahead and write something out here. Oops, atoms, molecules. Oh my gosh. Okay, so I don't see any questions. So essentially what the takeaway from this is we're going to get a whole bunch of conversion factors out of this. We're going to see that 1 mole of atoms or molecules, whatever we're looking at, is going to be equal to Avogadro's number in atoms or molecules. That's also going to equal the molar mass of whatever we're looking at in grams. So we can use these as conversion factors. So we can say, okay, I have my shot glass full of water. So let's say I have 45 grams of water. We're going to see that I can find out how many molecules that's going to be. By using these conversion factors. So by looking above, we can say, okay, we know, in this case, we're looking at grams and molecules, right? So we're not going to necessarily need moles right now. We're using these two. So we know that 6.022 water molecules will be equal to that 18.0 016 grams. Remember, we calculated this one up here somewhere. There it is. we saw that 1 mole of water was 18.016 grams. So we can use this as a conversion factor. So if we really wanted to see how many molecules of water are in our shot glass, we could do that. Just like before, we're going to have to use our conversion factor such that the unit we don't want gets canceled out. In this case, we're going to cancel out grams. So we're going to put 18.016 grams of water. And we're going to then put our number of molecules on the top. And going to our calculator, or in my case, Google. And so we're going to see that in our shot glass, you can amaze all your friends. We're going to get 1.50 times 10 to the 24th molecules of water. So however many in terms of like numbers, that is hexaquadrillion water molecules are in there. So pretty cool stuff. At this point in science, it's just kind of like party trivia at this point. No one actually cares about the number of molecules. Most people just care about moles. We're going to see moles are going to be a much better unit to work with because we can't really count molecules. It's kind of silly to do that. But we could also use this information to find out how many grams does one atom of, let's see, which element shall we do today? How about, let's do rhodium. So you're going to say, what the heck, where's rhodium? We go to our periodic table. I'm just going to tell you right now, rhodium is number 45 here. So we can go ahead and use the information here. So I'm just going to copy that number. So 102.905. 102.905 grams. I'm just copying the atomic mass there, or we can just say molar mass, same thing. So, remembering our conversion factors, that 1 mole is the same thing as, yes, I believe so. I don't have the syllabus saved on these computers that I'm working on, but I believe it should say on the syllabus. So this is chapter 3B that we're on now. If I had put that chapter 3B was part of exam 1, then yes, it will be. So, to answer your question. Okay, let's see. Okay, so if we go ahead and work with these numbers, we're going to start with 1 atom of rhodium. And so we're going to have to put something that has atoms on the bottom, right? Because we have to cancel out rhodium atoms. And we're looking for grams, right? So we look here. Let me just space out rhodium atoms because that looks like some weird, weird word. Okay. We have this number we've gotten from the periodic table. But we see here that we have grams and moles, right? What we need to remember is that 1 mole of anything, whatever it is, atoms, molecules, pancakes, whatever, 1 mole of whatever, is 6.022 times 10 to the 23. So we can go ahead and plug in those numbers. So again, from the periodic table, I got that grams. That was the atomic mass of rhodium. And we're going to go ahead and put our Avogadro's number down there. And we can go ahead and see how much one atom happens to weigh. So 102.905, 6.022 times 10 to the 20, not to the 23rd, or not to the second. Okay, there we go. So doing this number, we get 1.71 times 10 to the negative 22 grams. Okay, so really, 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 really small number, right? One atom weighs a very small amount. So now, or let me ask, do you guys have any questions on this one? Okay. So of these two, which one has more atoms? $50 grams of silver or 50 grams of gold? And this is not a trick question. They're not the same. We're going to have to see that we would technically want to convert these into atoms, right? We can take grams, convert them into atoms using our periodic table, right? But it may be easier to understand, okay, silver is here, 107.868 grams per mole, and gold, 196.9. Thinking about that, considering that silver atoms weigh less than gold atoms, then I will get rid of this S. So silver atoms weigh less than gold atoms. And so what we're going to be able to say is that because silver weighs less, it has a lower atomic mass, we would need more of those atoms to make up 50 grams. This is somewhat similar to the, like pound of feathers, pound of bricks thing. So I'm asking you, which one, has more of these? Are there more feathers? Like if we were to count all the feathers in a pound of feathers versus counting all the bricks in a pound of bricks, we would say, of course, there's a way more feathers than there are bricks, right? In terms of number, quantity of them. While yes, their masses were the same, they weighed the same, we're going to see that, therefore, 50 grams of silver atoms Ag rather, oops, has more atoms. So we can just, without having to calculate, we can also just kind of make these comparisons by ourselves. And we could do the same thing with molecules. I could ask you which one has more molecules. Is it this amount of water or this amount of carbon dioxide or whatever? And you'd be able to do the same thing. So using the molar mass of a substance is going to be a good way for us to kind of be able to say certain things about it. So we're going to see that understanding that different masses of different substances, or rather the same mass of different substances, would have different amounts of atoms for each is going to be very important for us at the very end of the semester. So all of you will forget this by then, but that's okay. We can work with it. Alrighty. So we do some more number crunching. Okay. Let's do another example. Looking at this one will not be as obvious to us. This one we are going to have to calculate, just because these are different masses now. So we can do so, right? We have already calculated, I've chosen these compounds because we have already calculated their molar masses, but if it were one that we hadn't, you'd have to calculate that molar mass. So molar mass here was 44.01 grams per mole, and this one was 18.02 grams per mole. Okay, just giving you the numbers there, but you might otherwise have to calculate them yourselves. Alrighty, so if we wanted to do all this stuff, we would say, okay, we're going to start with 50 grams of CO2, put 44.01 grams on the bottom, 6.022 times 10 to the 23rd on top. And for water, we would do the same thing with its respective numbers. And we would do all this math. Why am I doing this? This is not fair. I'm making myself do math. 23rd divided by 44.01. So doing that, oh gosh, how ugly. 6.84 times 10 to the 23rd. The next one, I've lost my mouse. There it is, okay. 30 divided by 18.02 times 6.022 to the 23rd. Oh, because I did not put a decimal point. Okay, is 1 times 10 to the 24th. So, hooray! This is the winner. We have more molecules in that 30 grams of water than we do in the 50 grams of carbon dioxide. So 30.0 grams water has more molecules than 50 grams of carbon dioxide. There is another way we can approach this problem without using Avogadro's number. We could have instead done 50 grams of carbon dioxide and just converted it to moles. A little bit easier on us in terms of calculation, just because nobody wants to type into their calculator 6.022 times 10 to the 23rd over and over and over, right? So we could have just done it in moles instead. And remembering that our molar masses are in units of grams per mole, we could flip them over and make it moles per gram. Just because I happen to do this one first, I will write that one, and then I'll calculate the other one for us here. 50 divided by 3.1. And that's going to be 1.14 mole. Okay, and remembering, yeah, I know, right? That moles, just like dozens, 1.66 dozen waters would be more than 1.14 dozen carbon dioxides. Remember, moles is just another fancy word to kind of take the place of that 6.022. So doing it this way, we're going to get the same result. And so we would see that our water would be victorious there. All right, because nobody likes to use 6.022 times 10 to the 23rd. Use moles instead. Moles are our friends. Alrighty, any questions on that? I understand that this is confusing, totally normal, but we'll keep doing it. The more we do, the better we'll get. And guess what? You'll have homework on this. Haha, hooray. What mass of platinum has the same let me not use platinum. Let me use let's just use water. No. How about nitrogen? Yeah, nitrogen gas, that'll work. Molecules as oops. Let's see if we can work on this one. Our last problem of the day. So we're looking for a mass of nitrogen, so that means we're looking for grams of nitrogen, right? And we want the same number of molecules as 50 grams of glucose. If we remember from before, we found that the molar mass of this was 180.2. So, looking at that, cotton shush, mister, we can say we're going to have to convert our 50 grams into molecules, right? And then take that number of molecules and use the molar mass of nitrogen to figure out how many grams of nitrogen that's going to be. If that makes sense. So, we always kind of want to start with things that we know, right? We have this stuff given to us, so we might as well use it. So we could say 50 grams of glucose is going to be equal to, calculation time, did that echo ever go away, by the way, or are we still having to deal with that? Just out of curiosity. It's gone? Awesome. Okay, cool. So I've left this one in moles because I really much never want to use 6.022 times 10 to the 23rd in calculations. Again, that's a pain in the ass to put in your calculator. Just avoid it if at all possible. So we want, with this one, the mass of, for the same number of moles. Let's see. So remembering that moles can be related to molecules, we can just skip over molecules entirely here. We could, if you want, go right ahead. Instead of putting 1 mole on top, do your 6.022 times 10 to the 23rd molecules. Have fun, knock yourself out. You'll get the right answer. It will be exactly the same. If we understand that, we say, okay, we have this many. I didn't round, by the way, just quite yet, because sig figs, since 50 grams is a measured quantity. 9.47835. We're just going to say moles of nitrogen now because we want them to be the same. We're going to have to put in the molar mass of nitrogen, right? Which I did not give you. And you can't put 14.01 grams, which is what you would find on the periodic table, because of this little pesky 2 here. That's going to be 2 times 14.01. Right, because I said N2. So grams is going to go on top. 1 mole on the bottom. Times 28.2. And that's going to be 7.77 grams of nitrogen, which is our answer. So we're going to see that 50 grams of glucose is going to have the same number of atoms, or molecules rather, as 7.77 grams of nitrogen. So, exciting stuff. We will continue doing this sort of thing tomorrow. I will look up on our thing, on our syllabus, to see if this was on the exam or not. And in Discord, I'm going to put a poll for us to see what kind of exam you guys want to do. If you want to do a multiple choice one, or like a free response one, or mixture, or whatever, we're going to see what you guys want to do for that. Does not matter to me. Okay, I'm going to go get ready for 101 or 111 now, so gotta go. Mess with me on Discord if you guys have questions or anything like that. I will try and upload these to YouTube. And yeah, so cool. Awesome. See you guys tomorrow.